content. This is the NRCS Irrigation Assessments of Wisconsin. The course is Wisconsin Engineering 39. And my name's Michael Isaacson. I'm the state hydrologist for NRCS and the hydraulic engineer. And in April, I will become the Southeast Area Engineer, which I'm excited about. So those of you in the Southeast, I'm looking forward to working with you and meeting you and all that. I have Beth Peterson on, our Assistant State Conservation Engineer, who will be moderating the chat line and stopping me if there's questions or telling me if the slides are off and that sort of thing. I am going to turn my video off just to save bandwidth. And but feel free to put your questions in the chat line, and if you want to participate in the discussion, please do so. This will be recorded, and so the recording is starting now, and it will be available to all of those on our SharePoint, and I also will share with Penny Pulley of the Land+Water, so that those of you outside of NRCS can obtain the video from her. These slides, I will distribute these slides as well, and so that they will be available. Our agenda today is to talk about reference materials on irrigation assessments. We're going to talk about the NRCS planning criteria regarding irrigation, also a little bit about irrigation systems, and then we will do an assessment of an irrigation system. We'll show how theory is used to evaluate applied irrigation. We'll learn how to assess a pumping plant and talk a little about variable speed drives. We'll determine the feasibility of some of the on irrigation planning, and then do a conceptual designs. And then we'll discuss the situation where we identify multiple operating points on the same system. Today's lesson is boiled down to Wisconsin. Irrigation is a broad subject. It's practiced throughout the world, many forms, many types. Irrigation is a historic practice. Wisconsin, I don't know if irrigation is so much essential. I think it helps vegetable growers guarantee a crop, and so it's more of an insurance policy. If anything, it's supplemental. But to many parts of the world, irrigation is essential. You just simply do not grow a crop without irrigating it in that. And so a lot of people come into the offices and they say, well, I got an irrigation system, and it's really hard for us to address their issues because irrigation is a supplemental practice in Wisconsin. And so I don't think we're as familiar with irrigation as they are in other parts of the world. But that's okay. I think it's going to become more and more important as people go to vegetable production in urban agriculture, and that irrigation will be used quite heavily by those sectors of our industry. And so NRCS is a leader in irrigation because of its role as a nationwide conservation service. Out west, everything is irrigated, and so water resource concerns dealing with water quantity and water quality are important. And as the role, NRCS has created many references on irrigation, and they are thorough, they're complete, they're well done. And I wanted to say that a good one is NEH 210 Part 623. And right now they have Chapter 2, Chapter 7, Chapter 8, Chapter 9, and Chapter 11. These are comprehensive references for irrigation. And so if you ever want to know anything about something, these are good resources to have. We have adopted conservation practices here in Wisconsin. And then another resource here in Wisconsin is the University of Wisconsin, Madison, the extension website. They have it's boiled down and tailored to Wisconsin and what we do here. I've reviewed it and found it to be of high quality and very helpful. They have a great presentation called Irrigation 101 that's done by same as that Stanford.
Got
And
Stanford.
it kind of gives a boils down those references and provides a great overview of irrigation. Yeah. In Wisconsin, we can have an irrigation water management plan. It's called DIA 163. It's very similar to what a nutrient management plan or energy audit. It's planning the irrigation systems and how to use it to conserve water and to reduce energy. And so that is available here as a contract activity. I don't think we have a lot of TSPs. In fact, I don't think we have any TSPs that do irrigation. So that's something that I'm trying to work with the university on developing some TSPs that can do that. In the meantime, this training here is to help us complete a 163 in-house. There's a few people around the state on NRCS staff that can do this, and so please reach out if you have a producer that wants an irrigation water management plan, DIA 163. And it's also in FOTG 3, we have planning criteria solely focused on irrigation, and many of the things that I'm going over today are located there. And if you go to that FOTG 3, you'll see a section called irrigation. So first off, what are the resource concerns regarding irrigation? And I talked about how irrigation is a worldwide practice, but limited in scope in Wisconsin, but these resource concerns are universal. I think maybe in the world they have insufficient water. That's really a big deal, and I think it's here too. Here we want to have, so resource concern is 10, insufficient water, inefficient use of irrigation water. And the examples are overwatering, underwatering, or your application rate is greater than your soil intake rate, which means you're going to have runoff, which means soil erosion and water quality impairment. You're also going to excessive losses, like if you're just spraying water up in the air, you're going to have evaporation and wind drift. And really specific to Wisconsin, because we get so much rain, is when you irrigate near a storm precipitation event. And so you might irrigate into the root zone, but then the next day you get a big storm and everything goes down to the groundwater. It impairs groundwater. And if you applied any chemical, herbicide, or fertilizer through the irrigation system, though, that's all gone now. And so these are resource concerns regarding insufficient water. The other one, which I think is more applicable to Wisconsin, is 27, insufficient energy use. And here, this is where farming, ranching practices and field operations, and there's a lot of places where there's insufficient energy use. And so oftentimes we do energy audits and somebody has an irrigation pump, and so the irrigation pump gets wrapped up into the energy audit, which is fine. But an irrigation pump, when you're looking at that, you have to look at the entire system. You just can't look at the pump. It's much more comprehensive because the pump is designed to meet a demand. And so the demand is what's dictating the pump, and it tells you whether the pump is efficient or not. Our examples here, and I show the first one is a pump curve greatly exceeds the system demand curve. If you're doing an energy audit on a pump and you don't understand what the system demand curve is, then you have no way to evaluate the pump. And so that's why you have to dig down into the demand to see what's going on. Another one is a system demand curve may have multiple operating points, and we'll give some examples later. Using high BTU energy source like diesel, and we'd like to convert diesel engines to electricity because of the energy savings. One thing that we don't really look at, though, but anytime you have a pipeline velocity that is greater than 5 feet per second, it means you're going to have greater friction loss than you should. Friction loss means more energy. And so a lot of times people say, well, we keep our pipeline velocities below 5 feet per second because we're trying to do surge protection. We're trying to protect that pipe. And that is not true. The reason why we have that standard is because of energy savings. It's a criteria NRCS has set up nationwide, and it's totally based on energy. In my private practice, when we had gravity pipes, I would have velocity of 7 feet, 8 feet per second on plastic pipe, and it works perfectly fine. I'm not saying that surge is not an issue, but it's not the reason why we have 5 feet per second. And I want to, in this training, eliminate that from our thought process. The reason why, because people will say, well, it's expensive to do less than 5 feet per second. And my answer is, well, NRCS is about saving energy. And so that's why we stick to that practice. It's not to protect your system, it's to conserve energy. The other examples that I see in Wisconsin is oftentimes we have a well and everybody thinks their well's big, and then they put a big old pump on there. And what happens is the well does not have the capacity for the pump. And so the pump, you got this big old pump, and then you got a little amount of water that's going into it. And, you know, it's just kind of poor sizing in that. And so there's a example of energy use because you could only run that pump at its operating point, and then you have to kind of turn it down to match the well capacity in that. So it's burning a lot of head. So in our planning criteria, this is in our planning criteria spreadsheet. If we have insufficient water as a resource concern, and there's a description right here, and we kind of went over some examples. We have some assessment tools that we could look at, and one is the FIRI, F-I-R-I, which we will talk about. It's a tool that's in the FOTG3. We have, this is kind of a DIA 163, I guess. It's a client input and planner where we look at. Another one is changing gross water applied, and then again, it's the FIRI. We have a water losses, which we could look at. I don't know if this is so much applicable in Wisconsin in that. It has to do with efficiencies. Usually we don't irrigate enough to save this much amount of water. Out west you do, but here, like a pivot will only we'll put on 10 inches, which is really minimal.
Mike,
yeah,
some of that is, it's the pipeline. It's if you've got a very leaky pipeline that when you stop pumping out there, it releases all that water. If you lose that much water from there, that's what they're looking at.
Okay, yeah. Usually, I kind of found this silly a little bit because usually if you have a leaky pipeline, that's a huge nuisance and everybody knows about it. In that, so
but that's where that's coming from, is if that pipeline's in bad enough shape that we should be replacing it because we're losing that much water.
Okay, thank you, Beth, for the clarification. And one thing we really do look at is the coefficient of uniformity. We like to have, that means that if you have a sprinkler system and you put a cup all over the field, you should get about the same amount wherever you go in that. And that's the definition of efficiency in irrigation, is we're putting water, the same amount of water over every square inch of that field. If we could do that, then we could reduce deep percolation because everybody's irrigating to the dry spot. It's not such a big issue in Wisconsin because you got a lot of rain, but out west on my lawn, I had to go irrigate to the dry spot. Otherwise you have brown spots all over your yard. And so that's what you're trying to do there. And we have catch can tests that do that. And you're trying to figure out your, if you're over 85%. Then the last one is in our standard, we have a lateral and sprinkler spacing. Oftentimes it's like in the winter when you have somebody come in, you can't do a catch can test, but you can go take some measurements on what their sprinkler system looks like. And you could use the standard here, CPS 442, to see if you have a resource concern or not. If it's outside the standard, it means the catch can test will probably be below 85%. These standards are based on years and years of practice and experience and research, and so they're well developed, and I actually believe in them. So here's the planning criteria regarding energy. When we have insufficient energy use, we talked about some of the examples that we have. I think we're trying to decrease the dependence on renewable energy sources through improved energy efficiency. There's a lot of room here in Wisconsin to help reduce energy when it comes to irrigation pumps or any kind of pump. I want to say this is applicable to all pumps. That the problem with energy in Wisconsin on irrigation is we just simply don't irrigate enough. We only irrigate, maybe we put on 10 inches. And so oftentimes the Pratt's, when we look at an energy reducing thing, it doesn't pay out. It's not economically feasible. If we were to put on 20 inches, it would be. And that, and we'll talk about that a little bit later. Our basic assessment levels is, again, the energy audits that we kind of, work at. And then we have some spreadsheets developed, and I'll be going that over today, where we look at a present pump and then a few proposed pump and see if we have a simple payback of 10 years, and then the energy savings, and if it also is within the economic life of the practice. As a rule of thumb, we're looking at trying to get 25% or more efficient energy savings from a pumping plant. And so there's spreadsheets on how to do that. And the one thing that we should look at is, again, our pipeline velocity. If we see a pipeline that's less than 5 feet per second, that's a resource concern. I think NRCS really wants everybody in the country to have their pipeline velocities below 5 feet per second. And so that's why we get involved. Interestingly enough, this criteria doesn't necessarily translate to a 25% energy savings, but it is an acceptable criteria for defining a resource concern. And so obviously it's important to Mr. NRCS, so it's important to us. Oops. So I want to talk a little bit about what is an irrigation system. And this is applicable to Wisconsin. Outside of Wisconsin, there's much more examples. It's a little bit broader, but here in Wisconsin, what I've seen is an irrigation system is usually a pump. The pump could either be a groundwater, hooked to a groundwater well like here, or it could be sucking out of a pond or a lake or a river in that. But usually you have a pump, and the pump is to pressurize the system. The pump always discharges into some sort of a pipe system, which we call pipeline or conveyance. And so here we have the pipeline going from the pump, and here we got a turnout that will go to a place where somebody could hook on a sprinkler system in that. And so that's what this looks like. And then at the end of the pump, we have what we call the application or demand in that. And so when we do an irrigation assessment in Wisconsin, and oftentimes we're asked just to look at the pump, we have to look at the entire system. And we're going to talk about why we do that today. So an assessment for inefficient water use only focuses on the application. And maybe it focuses on leaky pipelines. But as I said, when you have a leaky pipeline, you usually go fix it because it's causing some other problems on your operation. But inefficient water use is right here. And this is where we're looking at spacing, or we're looking at uniformity, and maybe we're looking at pressure differential on all kinds of irrigation, whether it's drip system or pivot. So application or demand is when we're doing inefficient water use. This is where we focus on. When we do energy assessments on energy, we got to look at the entire thing, because there might be energy savings over here. Maybe these sprinklers are 70 psi, and maybe they could be reduced to 40 psi. Well, that's a huge energy savings if we could do that and achieve the same application. Maybe the pipeline's size too small, so that we have 5 feet per second, or over 5 feet feet per second. Well, that's an energy issue. And then, of course, the pump may be oversized, or maybe so we could put a VFD, or we could change out the pump. And so the energy has to go for the whole system. And if there's a take-home lesson here today, if somebody comes into your office and talks about the irrigation system, and they're concerned about the water, this is where you focus on. But if they're concerned about energy, you need to do a comprehensive look here in that. I hope that makes sense. The important thing in our standards is that if I'm working on the pipeline, I got to make sure everything down here meets our standard. If I'm working on the pump, I got to make sure the pipeline in the application meets our standards. However, if I'm working down here, I don't have to really worry that these meet our standards. What I do have to worry is that they meet the new requirements of my system in that. And so that's something to consider, but it's not necessarily that it meets your standard. I think we could look upstream and say, hey, your pipe's not meeting our standards. You may want to look at that. But it doesn't forbid us from doing a practice down here. And when we're doing a 449, our standards allows for a bad irrigation system. The idea behind the 449, we talked about it last week, is that it should lead discussions on, well, you're over irrigating because you got a bad system. And so maybe you need to upgrade your system in that. And so you always look at, depending on where your practice is and what's happening, you have to look downstream. You don't have to look upstream, but you have to look downstream and make sure everything downstream is meeting our standard. So an assessment overview, we got 3 things we're going to focus on. The first one is how to assess irrigation application for inefficient use of water. And we use the tool FIRI or FIRI. Number 2 is going to how to assess pumping systems for inefficient use of energy. And number 3 is how to evaluate the feasibility of a VFD to reduce energy use on a pumping system with multiple operating points. We're going to first focus on the irrigation application, or FIRI. There's 3 things we're going to look at: is identify existing types of irrigation application. We're going to look at different kinds of irrigation systems. The second one is to select improvements to the irrigation application. And the third one is to identify impact of irrigation system efficiency. So first off, let's talk about the rating tool that we use, FIRI. It's a spreadsheet, and it looks like this. And hopefully you've seen this it's in a RFOTG 3, I believe. And it allows you to look at the present condition versus the planned condition. And so the input you have to collect when you go out to the field is you have to see what type of irrigation they're using. How are they scheduling irrigation? How are they maintaining the system? How is flow measured? This one's a very important one, and there's a lot of points in theory regarding this. Last week in our 449, I emphasized that when we're with our producers, we really need to get them in the mindset of investing in a flow meter on their irrigation systems. They'll be much happier with it. Everybody's going to buckle at the cost. They'll kind of drag their feet, but you never really have regrets putting a flow meter in, unless somebody's coming measuring you, and then maybe you will, because they're regulating you. But when it comes to operating and understanding whether your system is doing what you think it is, the flow meter is essential. We also look how skilled an irrigator is. And I know this is kind of hard because you don't want to say that somebody sucks, but you do have to kind of see how knowledgeable they are in theory. And then we're looking at the water supply, how reliable the delivery is. In Wisconsin, our irrigation systems are typically the same because our objectives are typically the same in that. And so water distribution control, we could say that all flow rates to each set are adequately controlled. And this is because we have a pump. We have a pump that supplies an application. You don't have shared pumps. So neighbors don't share pumps here for the most part. You might run into that. I'm not saying you won't, but usually the owner has his own pump and then their own applications in place in that. And so it's a tight closed system. So this is in theory, this is an option. This is what I would put. Our conveyance is always closed conduit pipeline. I don't see much open channel flow. However, on cranberry bogs, you will see an open channel flow on their lift system. But for the most part, irrigation, when we're looking at vegetable production or other corn and soybean production, it's a closed conduit pipeline. With that said, we don't have much tailwater reuse. And so for the most part, you could say 0%. And then our climate is always this warm, and our peak average is ETs as 0.30. So what Fury does is it scores a rating value for both conditions. And if you look back here at the spreadsheet, we will get a rating value right here for the planned condition, and a rating value for the proposed. I mean, the present and the planned, I said that wrong. And so then we look and see, well, is our planned practice, are we actually going to improve the current situation? And we try to say, yes, it's going to improve water savings by this much. And then that criteria allows us to get involved in cost share if it does. So here we have an example of a Fury system. And in this case, we're trying to see if we have a change in gross water. This is our planning criteria, greater than 10%. And in here, we got a 15%. And this page is on Fury. It's this next page right here when you have a detailed report. And so here is the inputs, and here is our detailed report. And so when you fill out your inputs, this will self-generate, and then you can see if you have a change in gross water of 10%. And so then we're looking at percent of maximum potential rating on the plant system. And here, the present system, we have an 80% here, and now we're going to 88%, which is greater than 85%, which tells us in this particular case that we could go ahead and cost share with the planned tool. Now, just because it doesn't cost share, just because it doesn't help here, doesn't mean that we don't give the landowner useful information in that. And so when they want to have an assessment on whether what they're doing is correct or not, or if they could find improvement, this is a nice thing to do. Because, you know, if this is below, you could say, well, you're not really going to pay for the benefit that you have. So you could say you could put your money somewhere else. If we do show that there is potential here, then it's kind of, this is feasible for you to do as a landowner, to invest in a new system. So this is how our data entry looks like. And we have our irrigation type, and maybe I'll go to the other page here, because you can see it better, I think. We put our irrigation type here, and there's scroll downs, and there's a whole bunch of stuff here you could see. And then, so you can pick one for the present or the planned. You got your measurement type, which we'll talk a little bit later: scheduling, scale, maintenance, delivery, and soil. And then down here are system design factors. Some of these may not, some of these we don't need to use. And that if you ever have questions on any of these things, please give me a call. I'd be happy to explain them to you. They're not easily understood just by the description. I think there should be pictures, and maybe that's something we'll work on in the future. So you put your data entry in this thing for both the present condition and then the planned condition. The present condition is what's out there, and the planned condition you can work with an irrigation dealer on what they propose to put in. So the types of irrigation that we see here in Wisconsin, and then what I have here is the current system or present, and then these are the things that what we want to point people towards. When they're talking about upgrading their irrigation system for improved water efficiency, this is what we do. We don't replace a traveling gun with a new traveling gun. That's like replacing your old Ford pickup truck with a new Ford pickup truck. In that's equivalent. What we try to do is, if you have a traveling gun, well, they come into our office and say, well, I think I'm not getting good water efficiency for my traveling gun. We say, well, here are some options. You could look at a solid set sprinkler, the center pivot sprinkler, or micro irrigation. So if they come in with a sprinkler pipe, we could say, hey, we could replace their sprinkler pipe if it's not meeting our NRCS standards. Meaning, like in a cranberry bed, if they're like an 80 by 80 criteria, we could actually say, hey, you got to increase your sprinkler density because of the pressure that you have. We can invest in those additional sprinklers there. The other thing, in order to meet our standards and get the uniformity that we need. The other thing with the sprinkler pipe, we could say, well, center pivot's a little bit more efficient, so we could go to that, or we could go to micro irrigation. If somebody comes in with a center pivot and they say, hey, I don't have inefficient water use, we could go in with, hey, let's look at your sprinkler package. Let's replace your sprinkler package. The other thing we could do, and Dr. Wang talked about this last week in our 449, is we could look at variable rate irrigation in that, and there's two methods there. This is quite a capital cost. It's expensive, but the NRCS is encouraging farmers to go that route because it saves water. And the other thing we could do is micro irrigation. So the top of the food pyramid here is micro irrigation. This is, I think, where we get the largest water efficiency achievements. And so what if somebody comes in with a micro irrigation issue? Well, what we look at is, well, does it meet our standards? And so we have to evaluate their system. And if I think we could help cost participate in a system, upgrading their system to meet our standards. And then, of course, the operation of all these has our 449, our irrigation water management. So those are the types of irrigation we will see in Wisconsin. And so just an overview of each one. Our sprinkler system looks like this. Our traveling gun, meaning you got the tractor and the hose, and it goes here, and then it pulls back, and then they go to this side and does the same thing. And these are the things that we can look at as a solid set sprinkler will irrigate that whole field at one time. The center pivot looks like this. The problem with the center pivot is you're going to lose these corners in that. And so farmers are a little concerned about what to do with these. And you know, there's options for NRCS to look at, and it's a land use option. What do you want to do with that land? You'll get much better yield in here, and for the same inputs, well, here you put the input, you get less of a yield. And so maybe there's something else they could do here with this land. You could always put a sprinkler system here too. So there's different options there in that. Micro irrigation can have the same footprint. And so I got some of the benefits here, and you can see them when you get the slides in that. But the idea, when it comes to irrigation conversion, the big things that concerned our land owners are footprint. They're also interested in labor, and they're interested in energy. That I think they want good uniformity because that means good yield. And so these things talk about some of the pluses or minuses of these conversions. Yeah. So if we have a sprinkler system, usually they're a lateral move, meaning you have one lateral. And so what you do is you just keep moving it along the field. Here you irrigate in the morning, and then in the evening you move it over here. And then the next day you move it over there. And then the next evening over here, and then finally over here. And then you wait a couple of days, and then you move it all the way back and do it again. This is what I started doing when I was 12 years old. I worked on a dairy farm, and I just moved sprinkler pipe all day. I was paid $1 an hour, and I was happy. That it's hard work, it's labor intensive, and so farmers don't necessarily like this. It is cheaper, and so they do like that. But when they come in, they're usually looking at this is too much labor in that. However, they do have a poorer application rate than other types of irrigation. So they may come in and say, I want to reduce my labor, but that's not a resource concern of ours, but a resource concern of ours is both energy and water use. And so we can look at these systems here, the same thing, a solid set, a center pivot, or micro irrigation. So if they come in with a sprinkler system, and a lot of the farmers here in Wisconsin, they put their sprinklers on top of the pipe, and they use these pressure sprinklers because they have corn. They got 14-foot tall corn, and they say, I got to get that water above the corn. I will tell you this, Wisconsin is one of the few places I see with overhead sprinklers, and it's because you guys here have plenty of water. Elsewhere where you don't have water supply, nobody in their right mind puts sprinklers on top of the pivot, even in corn, in that they get the water down lower to the ground. There's different technologies on how to do that. And that's maybe someplace we could look at. I think it's going to take a long time converting people to that, but there's great water inefficiency with the water high up on the system because you get more evaporation and more wind drift. And so when they come in with a sprinkler system, a center pivot, what we want to do is kind of look at the sprinkler package and see if we could reduce and convert from a high pressure sprinkler to a low pressure sprinkler. There's great energy savings in doing this and great better water efficiency use. And then of course the variable rate irrigation, it's like precision farming, it's just precision irrigation, and you could actually program your center pivot to irrigate water exactly where it's needed. And that's a technology that we can invest in. And then the other thing is converting this to micro irrigation. What I'm trying to get here is we never convert a center pivot back to hose gun. And Fury will not let you do that. Fury will not rate that well. And so here's micro irrigation. And I want to put a plug into we're going to have micro irrigation training in June 13th, where we're going to have an introduction class on what is irrigation. And then 14th and 15th, we will learn how to design the system. The 14th is going to be where we actually learn design. And then the 15th you could bring a project that you have, and our national experts that are coming will help us do the designs right then and there. But from this training, we should learn how to assess and evaluate a micro irrigation system. I had it kind of on the calendar in April, but it's going to be in June. And so we'll get some adverts out here, and there'll be some registrations coming up here. We got some experts coming in from California and Texas to help us out, and we're participating with the University of Wisconsin on this. I'm really excited about this training and so micro irrigation, it is suitable for almost all agricultural crops and field shapes. It has low soil erosion potential, highest potential water efficiency. It requires good water quality, and so that's something to consider. It does require high management in that, and so you just don't give a micro irrigation to everybody. They have to be detail oriented in order for it to work. And the other thing to be mindful, it has a high capital cost per acre, in that it's usually twice what all the other systems are in that. So usually farmers don't really put this on corn and soybeans. However, where they don't have enough water, they do in that. But in Wisconsin, I doubt it would be economically feasible. But where they will put it on is vegetable production, because it's highly efficient, and the vegetable production will pay for it. So flow measurement, water must be measured to use it efficiently, and this is a big component of Fury. And here's some different types. Here we got a propeller type. This is a saddle fitting that could clamp right onto a pipe. You just drill a hole in the pipe and stick this propeller in, and then put this clamp on it. And it has this battery here. It could last 3 years. It's like a watch. It's really efficient, and it measures flow accurately. For micro irrigation, they got these little things you could put on your pipe, and here's another one like that. These are called magnetic meters, and then down here is one that's typically used for a center pivot. and then it has inputs that could go to your control panel. And that I've installed many of these, and they're really good and really accurate. And the way you put them on is in your design. Usually, the manufacturer will give you the installation recommendations, what they have, but they usually recommend if you have a pipe diameter of 6 inches, then it's 5 times 6, which means you got to have 30 inches. With 30 inches of straight pipe upstream of the flow meter and 6 inches or 1x downstream of the flow meter. Irrigation scheduling is a big part of theory. This is called your management and skill level. And that's why we have them signed from a 449 when you do a irrigation system practice. And that will give you points in theory, because we're assuming that they're going to be following this, because we're going to be meeting with them a year from now, where before they may not be doing that. And so that scores well in theory. And we talked a lot about this last week. If you missed last week's training, please let me know, and I will get you it's on a SharePoint, but I can get you the video link and the slides to it. And so theory, skill, and maintenance evaluation. These are very arbitrary, I think, and they're hard to score in that. But what we want to do on skill set is we look at the observed current irrigation and we set goals for planned irrigation. The 449 can improve skills. And what we're looking at is it's when and how much to irrigate. It's the standard of 449. That's really what we're looking at. And so the present condition, if they just, I just turn it on when I think I need to, that's really, I'd say maybe lack of foliar attention, or if they don't fill the soil, they just look at the plants, maybe it's over irrigation. But if they're doing 449, then it's they're following this. This scores well in theory. This scores less. So on our maintenance part of theory, we got to be careful here, because sometimes we look at a 25-year-old pivot and it's maybe starting to corrode and falling apart. That's not due to maintenance. I would actually say that if a farmer's out there running a 25-year pivot successfully, that farmer is putting adequate maintenance in that. And so it's based on how well the systems are being used in that. And I will say, I've got to work with National on theory on this maintenance issue, because I'm not sure how this relates to water savings in that. If you have a leaky pivot, I guess there may be water efficiency, but it's not because of maintenance, just because you're replacing an aged pivot. And to me, that's not necessarily a resource concern. We don't replace people's trucks just because they get old in that. But what we do want to do is make sure that the operator knows that sprinklers need to be unplugged in order to replace your uniformity. Pumps need to be producing at the correct pressure and flow rate. That's why we need to have pressure gauges and flow rates here and flow meters here. If they don't have a flow meter, maybe we could say that there's not good maintenance. But a new system will, with the flow meter, will have good maintenance. We need to make sure valves are functional. We need to make sure the automated controls are functional, and that quality maintenance quality is based on evaluating how a farm maintains equipment. It should not be based on the condition of an aged system. So we really need to look kind of at their skill set and how careful they are at doing things. I think you look at other places on the farm to see whether things are being maintained or not, and that might give you an idea. So in delivery, the options that we have is right down here: demand limited rate, demand unrestricted, and range fixed duration. These are, I think, that will apply in Wisconsin. It's because Wisconsin pumps are used to supply irrigation, and then pumps are not shared with other farms and that. And so our choices are, if you have well and a pump and a pipe capacity that is below the system demand, meaning that your pump only spits out 5 gallons a minute, but your demand is 15 gallons a minute. Well, you got to share that. You got to move that system, those sprinklers around the field. And so that would be what you call a demand limited rate. So suppose you have a situation where your well, your pump, and pipe capacity are greater than system demand. In that case, you have demand unrestricted. That means they could turn that pump on whenever they want, wherever they want. They don't have to worry about moving things around. Here on this other one, they have to kind of plan it out in order to do this successfully. It's not the easiest thing. And there's a lot more labor involved with this. This one, they just push a button, turn it on, and everybody's happy. And then the other thing is in Wisconsin, we have optimal pumping times. Usually during the night when there's lower energy use. During the day, everybody's using the air conditioner and the pumping rates go up. So farmers oftentimes like to pump during the night or during low energy electric pumping rate times. And that would be an arranged fixed duration, meaning that they're going to irrigate every day from 10 o'clock at night to 6 in the morning in that. And so if that's the case, then you got to put pumping scheduled for times with lower pumping rates. Now, just to avoid confusion, each one on these slides, when it says delivery, that means it's part of, like right here, there's a delivery right there. And so you could see, there's my options. And so I kind of talk about the options. So when I share these slides with you, you could actually see the options here. Okay, so wind and impacting sprinklers. We do have wind in Wisconsin, and when you have wind, it does impact sprinklers. When the sprinklers are on top of this pivot, they're much more susceptible. When they're closer to the ground, they're better protected. And so that's something to consider. You may ask, well, how do I know my wind speed? Well, if you click on this site, this link here, this will take you to the, it's actually University of Wisconsin does this, but Iowa State has this, and it gives you the wind speeds for different regions of Wisconsin and so you can look up for your area what your wind speed is. And you want to look during the irrigation season and see what it is. It's different from the winter to the summer. And so on the Fury, they'll ask you whether you have a medium spray or a fine spray or a coarse spray. And so this is just a genuine rule of thumb. If you have a medium spray, it's 30 psi on an impact sprinkler and 60 psi for a fine spray. But on a pivot drop sprinkler, coarse spray would be less than 10 psi, medium spray 10 to 20 psi, fine spray greater than 20 psi. Your flat plate has finer droplets, your groove plates have larger droplets. This has a impact runoff. The coarser your spray is, the more susceptible to runoff you will have. The finer spray, the less runoff you have. If you're designing your pivot for runoff in mind, you have to kind of consider this stuff in that. But Fury considers it as well as inefficiency, because what it's looking at is evaporation losses and also wind drift. So you put all those inputs in, and then Fury will give you your score. And so here's the options in that. And usually in Wisconsin, we enter about 10 inches. And it gives you right here how much estimated changes in gross water application. In this example, it's a little bit less than 10%. So this necessarily won't be able to meet our criteria. So that's water efficiency in Fury in that. Is there any questions there while I take a little drink? All right, if there's no questions, I am going to.
There's one question in there, but it pertains actually more to what you're getting into right now. So I'll bring it up after you get into the energy side.
Okay. Very good. So here are our standards to improve energy efficiency in that. So we have an irrigation pipe, and what we're looking at, we've already talked about, is pipe velocities with less than 5 feet per second. We have a pump powered by diesel engine, and so what we're looking at is a conversion to electrical pump. This is a given right here. You could, if you're going from a diesel pump to an electrical pump, you will have an energy reduction of 70%. This is according to BTU, that's British Thermal Unit in that. And so I don't know if you really need to calculate this. Everybody in the industry understands this in that. Maybe there's some way we could put this in so you could just say it's around 70% and that. And Beth, maybe you could help me with that.
It was kind of an assumed that
Okay.
the same way. I think we had our pump efficiency spreadsheet. You could show it there, but I'm not sure if it's totally necessary. Again, I'd have to pull up the cookbook. The comment, though, I'm going to go off of it's that line specifically. The cost of, Matt made a comment, and it's very valid. The cost of running electricity to that electric pump can be very high and sometimes cost prohibitive to the electric motor. We find that just because of location and how far they have to run the electricity, sometimes, yes, it's an energy reduction, but the cost-wise it's not an actual option for that landowner.
That is correct. And you're talking about a capital cost of getting a power line out to the
Correct.
pump.
Yep.
And that. And, you know, maybe down the road, NRCS will recognize that and say, you know, we could cost share on that power line as an energy reduction. But right now, that's not our game in that. And so, but I've been to many pumps where they would love to do that, but nobody could pay for it. And it's hard to take a power line 2 miles to a specific point when that's the only demand there. The power company wants you to pay for the whole thing. So understand that. The next one is pump which does not meet system demand well in that. And we got several options there. And this is where we'll talk about matching the system demand curve to the pump curve. We could either replace the pump, we could add a variable frequency drive. Maybe it's a pipeline that we could replace, or maybe we reconfigure the demand to match the pump better. There's all these options to consider. And then the fourth one is maybe a system demand curve has multiple operating points. I call it multiple demand points. That's really where a VFD comes in play in that, because a VFD could be added and there's potential energy savings there. And so we're going to go to our second assessment, which is how to assess the pumping system for inefficient water use of energy. So if somebody has an energy audit going on and they got an irrigation pump or any kind of pump, it could be a milk parlor pump or a sewer pump and stuff like this, we really need to look at the system. You can't just look at a pump at it by itself. So you got to develop a system demand curve, and you got to look at a pump curve, and then you got to compare the system demand curve to the pump curve. From that, you could identify the resource concerns. I don't know how you do it without doing that. I just have not figured out how to do that. Then you could calculate power requirements. You could look at pump affinity laws. That's your VFD when you're getting into the affinity laws. And then you could start selecting improvements to the pumping system and such. We've developed a new pipe size spreadsheet. There's an old pipe size spreadsheet that's based on that. And I keep trying to get it out and I keep finding little errors with it. And so I apologize for not having it out. It's under review. It does look like this, and you'll recognize the system on our spreadsheet. And here we got a system demand curve, and the green line is a pump curve, and we're trying to match this. But what I'm doing is one for a present pump and a planned pump, and it will have a place where you could feasibly try to figure out the feasibility of the system. Okay, and it does have pump cost data, which is really hard to get. We've populated our pump costs and got pump curves so that if you put a pump in here or a VFD, it will give you the cost so you can see what what your capital costs will be. And we'll try to get these updated at least annually so that they'll be up to date. This is really a nice tool for us to provide in data for our users out there. So let's get an irrigation system to figure out how to do a system demand curve. And this is from our reference, NEH 210, part 623, chapter 8 on pumping plants. And so here we have a pond, and somebody put a centrifugal pump to this pond, and they're sucking water out of this pond, and they're shipping it uphill. And suppose they have an irrigation system up here, a sprinkler lateral system right here. Suppose their flow rate is 500 gallons a minute. So the pump is 500 gallons a minute. That's the Q on a pump. Each pump needs a Q and an H. Q is flow, H is head. Well, the pump is based on what all these sprinklers are needing. So you got to add them all up, and that's the flow rate that you get is 500 gallons a minute. Well, your H is, you got to figure that out. And so I got 6 things here. The first one is the elevation difference between the water supply and the pump, and that's 13 feet. So that's my H1 right there. And I got number 1 here, static suction, 13 feet. The next one is 2, which is the friction loss in this pipe from here all the way to here. And so I calculate that up and I get 10 feet. That's number 2. The third is the friction loss between the 6-inch pipe right here. So I calculate that up and I get right here 8 feet. Then the fourth one is the friction loss between this, for this 300 feet of 5-inch pipe, and that's right here. That's 16.3 feet. Notice it's greater than the 6-inch. 5 inches is a smaller pipe, 6 inches a larger pipe. And so naturally, you're putting the same flow rate, you're going to get more friction right there. Then the fifth one is the elevation difference between the pump and where the demand is, and that is 30 feet. And so I put 30 feet right there. Then the sixth one is the pressure requirement of the sprinklers. And suppose that the sprinklers are 50 pounds per square inch. Well, 50 pounds equals 115.5 feet. You divide 50 divided by 2.31 equals, 50 times 2.31 equals 115.5 feet. So I have all my H's here. And so all I do is sum them up. So here's my sum line. And that equals 192.8. So the system demand here requires a pump that can deliver 500 gallons a minute and 192.8 feet. So on my spreadsheet, this is what it looks like. I already talked about that, and we're in the process of revising it. If you need, it's actually workable now, and some of you have already been using it and testing it out for me, and I'm happy to share with it now. I'm just not going to put it publicly yet. So give me a call or contact me if you want, if you're working on a pump and I could work with you on this. And so there we plot the system demand curve. And so for 500 gallons a minute, I have 192 feet. Now, in order to get the system demand curve, you have to also do the same thing for 400 gallons a minute, 300 gallons a minute, 200 gallons a minute. And you can see there's different H points here. And it actually at 0, this here is pretty much just your elevation difference between the water supply and where the demand is, the elevation difference, okay? And then up here, 600 gallons a minute. And you may say, well, this is a lot of work. Well, the spreadsheet actually does that for you. All you have to do is put in one operating point, and it populates the rest of these based on the pump demand curve. It's really a nice spreadsheet, and I have to give credit to Matt Blahowiak, who's on this call. He was the genius that actually came up with that system, and it was well thought of. I've never seen something like that in my career, so I was tickled pink when I saw that. I want you to notice that the head is dependent on the flow. And the reason why is because as it goes up, this is friction. So the difference between this point and this point is all just due to friction of the pipe. So what is a pump curve? The pump curve is given by the manufacturer. When you go to the pump store and say, I want a pump, and the pump store will first say, well, what's your demand? And so you tell them and what you're trying to do. So they will come up with your demand, and then they go to their catalog, and it's usually digitized so they can do it on a computer. But in the old days, they had to go to their catalog and they start looking at these pump curves. And so they're trying to fit the pump to meet your system demand. It's very much like going to the shoe store and they come out and they measure your foot, and then they go in the back and they look to see what kind of shoes will fit your foot, and they come out with the shoes and they see how it fits. Same process here. So that's what a pump curve does, is you see we're just trying to match the system demand. And so here you have head and here you have flow. It's the same thing as the system demand curve. And so on this particular system demand curve, I look here and I look and see, well, this curve right here, curve E, fits our system demand curve. And so then I come in here and I put in my pump curve. And in our spreadsheet, it's easy to do that. You come over here and you put in your pump curve in this area. Okay, so it's really simple to do. Here you build your system demand just by putting the pipe length, elevation differences, and stuff like that. And the spreadsheet will do that. And pretty soon it will calculate your pump curve and you'll plot your pump curve and your demand curve, and it will tell you where the operating point is. So now we compare the system demand curve to the pump performance curve. And so we got the pump curve right here, and we got the system demand curve. And the difference, they actually intersect right here. So on a 100% efficient system, our operating point will be right here. Well, unfortunately, very rarely will you ever achieve that. It's just like finding the perfect shoe that fits your foot perfectly. You'll never find that. You always get a blister on your foot because there's little room in your shoe in that. And so there's a little space here, which we call excess head. Our pump curve is right here at 192.8. I mean, our system demand curve needs 192 feet, but our pump curve is at 197 feet. So that we're burning 5 feet of head using this pump. Now, some may say, well, that's close enough. We're not going to get much better. So we shouldn't do much more. Maybe you got a guy that says, I could do better. Well, what can I do? Well, you could select another pump. 2, you could trim the impeller of this pump and dial it down right down to that level. 3, you could use a VFD and get right down to that level. And 4, you could change the system curve, meaning you could come here to the curve and then do something different there. So there's 4 different options there. So maybe on that system, that pump's designed pretty good for the system demand, but maybe your landowners, hey, I really want to look at this. What can you do? So you start looking at the system and that, and I look here. I can't change the elevation head difference here. I guess I could dig this pump, make this pump lower, but I can't change this elevation. So you really can't change elevation. So don't look at that. I could change this pump intake, and maybe I should have here. I didn't do it in this assessment, so that's bad on me. But I look here at this 400 feet of 6-inch pipe, and my velocity is 8 feet per second. Well, that's greater than 5 feet per second in that. Well, I could change that. I look at this 5-inch, and I know that was a resource concern, and the velocity is 8.17 feet per second. Well, that's greater than 5 feet per second, so therefore, it is a resource concern. Then I look here at the sprinklers, and they're using 750 psi. Well, my irrigation dealer tells me that, maybe there's a thing I could convert that to 30 psi. So I come down here and I prescribed suitable practices. So I'm going to make this a 6-inch now. An 8-inch, and I'm going to replace this section of pipe with 8-inch, and I'm going to convert this to 30 psi. And so I recalculate my H, and remember, before I had 192.8 feet. Now, by doing these systems, I have 124.9 feet. So I have a potential of reducing head by 35%, which will translate to energy savings in that. Any questions on this? I'm going to stop here because this is really important.
Yeah, Mike, what do you do when you don't know much about the sprinkler package? You know, it's an old sprinkler. It's been out there for 30 years. The guys, everyone's thinking maybe it's not very efficient. Do you use do you start with the sprinkler package and kind of work backwards, or?
Yeah, you could start with the sprinkler package and work backwards, or you could start from the supply and work forwards. Either way works, but a sprinkler package that you don't know what's going on. First off, you could do a catch can test to see the uniformity. Second off, there should be a pressure gauge, and the farmer will know what pressure they need. And so that could tell you whether there's some different options of lowering the pressure. And that if you have an impact sprinkler package and they need 60 pounds of pressure, you know you could put a drop on there and lower the pressure. So from an energy standpoint, you're looking at pressure. Is there opportunity and potential? From a water use standpoint, you're looking at really a catch can test to assess the uniformity of the sprinkler package. So those are the two things you look at.
Matt just made a comment that you're adding, just clarification, that you are adding both the static and the dynamic losses in energy that pump has to overcome. And that's why those are changing so much when the friction loss and things when you're changing those pipe sizes.
That's correct. And so very good observation. So when I look at number 1 and number 5 are statics, and you can't change that. I guess you can go to God and say, hey, can you lower their field? And maybe he will, or you get a big bulldozer and do that. But that's not practical, nor is it even something we would want to do, is disturb the soil like that. In that. So you can't change static, but so what we're looking at is dynamic things. And this is a friction, that's a dynamic energy use. This is friction, that's a dynamic energy use. And this is pressure requirement. And that you could argue that that's a dynamic thing, because you don't have to use the sprinkler nozzle that you're using. There's other options out there. And so you're just kind of changing that.
I guess, Mike, I like how it's all laid out. I think the one critical thing to look at before a person gets too far down the road is that the flow rate meets the peak consumptive use of the crop. Because we've gotten that pickle many times before where the guy wants a different pump. That's the reason he came into the office. And you start working out a system. And when you're done, you find out, wow, when I take the flow rate divided by the number of acres, he's at 14 gallons a minute. And you're like, that's almost twice the peak consumptive use of most crops. And so most people that are working with centered pivots know it's somewhere around 8 gallons per minute per acre.
In Wisconsin, it's 6.
Okay. Okay, great. So that's a great place to start. If he has a pivot out there and you're trying to evaluate a system that's providing more flow than that, you got to go back and work back from what does the crop need. That's what this is all about, is supplying enough water to meet the peak consumptive use of the crop. So take 6 to 8 gallons per minute times the number of irrigated acres, And if you're trying to provide more flow than that, you got a problem. He might say, well, I've been, say that comes to 500 gallons a minute, you know, and the guy wants 700 or 800. Well, maybe his nozzles are burnt out, you know, or maybe he doesn't have, he's got some elevation changes in the field, or he doesn't have the right, he doesn't have pressure reducers or something in there that's driving. It's a root cause of applying more flow than he needs. So to me, the big number on your screen here, Mike, is the Q. Because this is irrigation is a water, first and foremost, you got to be looking at water savings and try to get that where we can get it. Secondly, then we take a hard look at energy. But meeting that peak consumptive use of the crop, getting the flow right, is pretty important. Once you have the flow, most of these pivots are providing it with what, Mike, with these days with good pressure regulators, it's what, 30 to 40 PSI, 35 to 40 PSI. So we're trying to deliver between 6 and 8 gallons per minute per acre. And with a good sprinkler package, you should be able to deliver that with 30 to 40 PSI at the pivot. So if you, yeah.
That's
Right.
correct, Steve. And our first assessment on the irrigation system is that inefficient water use and the theory there. The theory actually does look at consumptive use. This training, I don't have any slides on how to do that, and that might be a future thing to do. The 449 is actually where we calculate our water use, because we actually look at the crops that we're doing, and we're looking at the available water capacity of the soil or the intake rate of the soil, and we're trying to target an irrigation there in that. But you're exactly right here. This Q here, that may be inefficient use of water, but it translates to inefficient use of energy as well. The other side of that is the water supply. And it's not necessarily if you got a pond or a lake, but it's more applicable if you have a well, because wells have a specific yield of their aquifer, you know, where the screen is placed in the well. And sometimes it's not an exact science. And so, you know, a lot of well drillers think they're all state and they can get you all the capacity you want, and they drill the well and all of a sudden it just drips out instead of gushes out. And you're going, well, I don't got enough water now. And so that's the other thing to look at here. You know, we went and bought this big old pump and it doesn't match my well capacity. And so that's another huge issue. Well, does your well capacity meet your system demand? Well, no, it doesn't. Well, why are you trying to do what you're doing? That's a serious question to ask them.
Yeah, I appreciate that, Mike, because I don't want to create crime number one, and that is when you're using cost share to provide assistance with the most efficient pump and pipeline for an erroneous flow rate and head, you got the load wrong. So we probably should focus on that on the next one, Mike, is looking at peak consumptive use and just double checking to make sure that the farmer isn't asking us to provide a level of efficiency for a flow that's
That's correct. And the most important thing, and I should have put that in the slide here, is ET. And so that's the other thing to take home from this is ET, evapotranspiration is what you're looking at. It's the demand, that this Q. It dictates what all these sprinklers are doing and whether we're meeting it uniformly. And then whether we have a supply enough to do that. It doesn't make any sense to really under irrigate gardens. In Wisconsin, you could do it, but out west, why would you ever invest in something you can never fully irrigate? It's just a bad use of resources. So.
So Mike, I just want to let you know everybody can't access the chat right now. So I just wanted to offer to anyone out there who can't, please, please send it to Matt Lahoviak or myself. Either one of us can bring it up. I'm not sure what's causing the chat issue, but I just wanted to let you guys know that.
Thank you, Beth. So now we did this. We replaced the 6-inch with 8-inch, and we changed the sprinkler nozzles. So now my system demand curve, here's my original system demand curve, this red line with blue dots. Now my new one is down here, but my pump curve is still right here. And so, yes, I reduced head by 35%. You can see it dropped from here down to here in that, but I don't have any energy savings because I'm using the same pump. So here's where my potential energy savings is the difference between this line and this line that I have. In order to do this, I have to do something with the pump, and there's two things I can do. There's three things. I could replace the pump, I could trim the impeller, I could add the VFD. And I should add, replacing the pump means I could take, if it's a turbine, I could take out a ball. But I could modify the pump. Maybe that's a fourth thing that's here. But I do not, I might get a better system demand curve that reduces head, but I do not achieve the energy savings till I do something with the pump curve. So here, if I did a VFD, what the VFD does is it slows down the pump, and so it moves the curve down to here, and I could dial it right onto here, and therefore I achieve the energy savings. If I replace the pump option, then just like the shoe store, suppose you got an operation and cut off your toes, now you need a new shoe. Well, the guy goes back in the back and picks a new shoe box out. Well, it's the same thing here. We go back to the pump store and say, well, my system demand curve is down here. Can you give me a new pump? And they come back and say, okay, here's the new pump right here that will do it. And notice it's not exactly perfect. So you're not going to get the same energy savings you will on a VFD. There's always going to be a little bit of wobble here in that. And so you got to, it drives engineers nuts, but it's just a reality of life. You can never really get this exactly close just because of the constraints. And so here are the equations that I have, and this comes from chapter 8. You could find out, go read the reference. It's equation 8.3 on how to calculate water horsepower. Our spreadsheets has it. It's a really simple equation. And so you could do this with a calculator out in the field. You could look smart in front of the landowner if you know your flow and your age. You just divide it by 3960, and that's your water horsepower. That's how much the demand needs. That's what the demand requires, is a way to say that. Well, there's the inefficiencies in pumps, and so the brake horsepower, what the pump needs in order to deliver this power that the water needs, then you have to divide it by the efficiency of the pump, and here's how you do that. So we start with a 24.9 horsepower water power, then we divide it by a 70% efficiency pump, and so we need 35.5. Well, then what does the power company need to provide to you? Well, it's right here. There's an efficiency on the motor, and so we have 37.4 horsepower. And so why that's important is because in our work, we need to calculate energy savings in that. In order to go to the kilowatt hours is what you pay for. You times the horsepower by 0.746, and then you also times it by the number of pumping hours. So in this case, if we were using this pump for 1,000 hours that year, we would be using 27,903 kilowatt hours in that. And this is for that higher head. Now, notice this is 197 feet. My system demand curve was 192. but I can't use this 192 because I'm using the pump, and the pump curve is 197. I've got to use the 197 from the pump. That's a common mistake when people are making this calculation in that. And so in design, we always use this. I mean, we use the system demand curve, but when it comes to actual operating costs, we got to go fit the pump. And so we got to use this one. It's a little bit higher. And so we use that 97, I guess the 197 rather than the 192. Our pump affinity equations are equation 8.4 and the equation 8.5. And there's two ways of doing the affinity equation. This is really one of the remarkable things of physics, is that this equation works out. The angular rotation of your shaft is a direct impact on your flow. That's a powerful relationship. I don't know how it could have come out better in that. And then look at this ratio. Then you could translate to the square root of your heads, and then the cubed root of your horsepower. And so if I'm over here and I need a change of flow rate, to a system demand, all I have to do is slow down the pump, and I could calculate all this stuff. Well, the same thing comes when you trim the impeller designer. The impeller is the fan inside the pump that goes around fast, that pushes the water through the pump and lifts it up to a higher pressure or a higher elevation in that. And the same thing, and so it has a diameter from the center point of that impeller to the edge of that impeller. So all I have to do is take that impeller out of the pump and go to a grinder and start grinding it down, machining it down to where it needs to be. And it has the same sort of proportion as the slowing, this RPM. I just want you to appreciate that, because whoever did physics here, they made this calculation really easy. And so while VFDs seem complicated, they're really simple to predict in that. And so it's just a nice equation. So here are the examples from our system. So if I was trying to go from 542 gallons a minute, which is what that pump was doing at the pressure head, down to 500 gallons a minute, then it reduces my energy from 26.5 horsepower to 20.1 horsepower. Likewise, if I had a 12-inch diameter impeller, I could grind it down to 11.06 and I get the same savings. So then we look at the feasibility of doing this. We're going to rate everything at 500 gallons a minute. And here I got my present pump with my power right here at 37. My present pump, if I could add a VFD to the present pump. I don't have to replace it with a pump. That's one of my options. So this one's running at 1600 RPM. This one's going to run at 1274 RPM. I got a 49% energy savings because all I need is 18%. What I'm trying to do is shift my head from 197 feet down to 125 feet. Okay. Well, I could also replace it with a pump and that. And so this is replaced with the same pump. I mean, a different pump, just a different curve. And this is what I get, but I only get 25% savings because my HP here's about 28. Well, then I could say, well, what if I replace a pump, but I trim the impeller of that pump, or I set the VFD to 1475 RPM. Well, here's the savings, 43 and 43. You can see I don't get as much here in this option as I would if I just put a VFD on the present pump in that. And so in this case, my economic feasibility here is actually right here, because here's the payback. And again, I got the capital costs here for each of these options. I got the kilowatt hours here, and the new spreadsheet will do this. I got my energy savings here, and the total savings here, and the payback by years, and I could say whether it's feasible or not according to our economic life. Usually a pump in economic life is 15 years and that. So yeah, this pays for itself and that. Now, when we do feasibility on energy savings, remember, we never really assess the feasibility of replacing a pipe with that's greater than 5 feet per second velocity. And that I don't know why we don't do that, but that seems important enough to NRCS to not do a feasibility. They just say 5 feet per second. So that's a resource concern we could address right away. But on these energy criteria that we look at, there are specific savings that we try to do. You know, you got to pay back within the economic life, and you got to have that 25% energy savings. So these are the pump curves that we have. They're from RS Means. Steve has a account there, and so if you need to access anytime to RS Means, there's a way and means for you to do so. RS Means is a great way to get costs on almost anything that we do. And that I have to credit Nicholas McNamara for populating this for me. He went and created these curves, and so we do have capital costs on pumps. This one's for a centrifugal pump in that. And, you know, over time we kind of ground truth these, but RS Means is pretty good in my past experience in that. And so the spreadsheet will actually extract a cost off this curve, you know, for the pump. It fits pretty good in that. And so I have one for turbine pumps, centrifugal pumps, submersible pumps, sewer pumps, and VFD. So there's costs there for them. So now we go to our conceptual design and so of the system, and assuming that our ET is correct, and in the when you do the 449, you will be assessing your ET and consumptive use. But assuming that that system is correct, what we would want to do here is we'll keep the pump. We're going to replace 400 feet of 8-inch. We're going to replace a 6-inch pipe with 8-inch pipe. We're going to replace this section of 5-inch pipe with 8-inch pipe. We're going to replace the sprinklers with low pressure sprinklers so we can reduce from 50 psi to 30 psi. We're going to add a VFD to slow down this pump so that it meets better. And our resource concern is we're going to reduce our energy by 49%. So now I have resource concern. I could work out an application with the landowner, and we could go from there. Everybody's happy if they get contracted. This morning I realized I didn't look at number 2, and so I could send this up. I had to send this up to Steve Becker for his approval, and I go, Mike, how come you didn't look at this section right here? And I'll go, oh, you know, I need, you know, there is savings right there because this is a 5-inch pipe. I could probably increase that and get it below 5 feet per second and probably do a little bit more here in that. And so do your best to do a conceptual plan and realize when you send it to other people for review, they have good ideas too. And don't be defensive of your work. Be appreciative that multiple eyes make for a better quality product. So points to consider when you're doing this. Typically, pumps are slightly oversized to compensate for wear. So I did talk about you can never size it perfectly just because the pump is not there. It's not available. But typically, dealers will oversize because they don't want the owner to come into their shop every year and say, hey, my pump's not working or it's not giving what I thought. So what they're doing is pumps, you know, when you pump in surface water or groundwater, you're always bringing sand through it. And that sand is sandpaper, which reduces your impeller size. And if you remember from our affinity equations, when you reduce that impeller size, well, you're reducing your output as well. So they do oversize for that. Also, the bearings, you know, they get, they lose their efficiency. And so you lose output there. There's also uncertainty. And then when you give some guy a pump or some person a pump, you know, in 10 years, they go, you know, I'm going to do this with my pump too. And they add another demand to it. And so our dealers tend to, they don't want to have a owner that's displeased with them. And I've had several people, well, what do we do with that in our RCS? Because, you know, we're trying to incentivize people to pick the best pump and try to get as close as you can to them. And one of the thoughts I've had is, well, maybe we just pay for the pump we specify. If we specify a 150 horsepower pump, that's what we pay for, even though a dealer may say, well, I'm going to put 175 horsepower because this guy's going to add an onion field in 10 years. So, you know, that's a discussion that we can have, and I think that you could talk with your area engineers on how to do that. But I just want you to understand that typically when you go to a dealer, they will come back with a bigger pump than maybe what you specified. That's why it's really important for us to design.
Anyway. There is a hand that's gone up a couple times. Bethany, did you have a question?
Yeah, actually, I was curious if the calculations are accounting for the loss of efficiency due to the VFD. Because we need to derate like another 5% because the VFD is put on there.
So the example I showed does not in that, but yes, you're right.
And then another question I had is, for these systems, if we're decreasing our overall pumping needs on a consistent basis, wouldn't it be more cost effective and actually more energy efficient to replace the pumping plant with the properly sized pumping plant rather than put a VFD on, which is potentially going to shift that curve way off what our optimal curve is?
So that's a good question. And Dr. Bert out of Cal Poly Tech, I was in a class and he gets asked that question all the times, is in the purist would say, well, just get a better pump and do that. And what he's saying is, to me, it's a capital cost. A new pump costs way more than a VFD. And so when you're lowering the VFD, you're getting energy savings, but at a much lower capital cost. So it becomes a question of economics there in that. Yes, you're pumping maybe at the proper curve, at the full RPM curve, you're getting a 70% efficiency. And so when you move the curve down to say a 75% RPM curve, you're only down at a 50% efficiency. That's true. But the net result is you're still saving kilowatt hours in that. And so his take on that philosophically, and he actually reviews our NRCS standards and reviews our references, is, well, what's the deal there? You're still getting energy savings. So yeah, it's not optimal, but you're still getting what you achieve, and it's economically feasible. And so we got to understand the cash flow. And maybe a farmer wants a new pump. And last year I ran a farmer who doesn't want VFDs because he thinks it's poisoning the land. And so there's, you know, then there we go to a new pump. But to answer your question, Bethany, is either way we're getting energy savings. And so how we do it is probably going to be dictated on the cash flow of our farmer, which is economics.
Okay, thank you.
Bethany, one thing I could see is having multiple, like 2 options maybe for those issues that you come upon, because it might be that the landowner decides that, you know what, I want to do it the right way. Yes, it's going to cost me a little more, but my pump is on the older side already, things of that sort. So I think having 2 options within the audit wouldn't be bad. And then having that conversation with that landowner so they can decide. I've seen people try to just put a VFD on everything instead of looking at the other side of, could you just get the right size pump? The VFD really comes into play when you're trying to feed multiple systems with different demands off that same pump, in my opinion.
Right, and that's generally what I find, that there's pretty limited cost savings from a VFD unless we actually need varying pressure or varying demand in gallons across the field, or different pivots that are all connected.
Yeah, same.
Okay, thank you.
You're absolutely correct, Bethany, and that's the last section of our training, is what to do with multiple operating points in that. One thing to consider is you know, trimming a pump impeller is fairly it's a cost attractive. It's a nice option to look at. But once you trim your pump impeller, it's final. You can't go back in that. And so you got to make sure that the landowner is okay with that before advising this route. The other thing to consider is VFD calculations using the affinity equation are theoretical. There's a lot of uncertainty when in your measurements. Things change over time, pump wears down and stuff like this. And so actual savings, when you go out there and you predicted if I set the VFD to 85%, it will achieve what I want. And all of a sudden you're down to 70% or 90% and you're all afraid that your calculations are wrong. Just take with a grain of sand. Don't sweat over that. In practice, what I'm hearing is that you'll get close, and if you get close, that's fine. And then the last thing, Bethany alluded to this, more energy savings can be realized if the pumping scheme has multiple demand operating points, and we're going to get to that now, which is the third part of our assessment. So the first part we looked at the irrigation system, and this kind of talked about where Steve was, consumptive use. Is our irrigation system meeting demand efficiently? And so we got to look at that. The second part of it is looking at the pumping system, and we're looking at energy use. And then the third part is, we'll dive down deeper into the energy system and see if there's multiple operating points. I would say, like on drip systems, sprinkler systems, big gun system, this is not necessarily the case. This is more on a center pivot. There may be other things, different scenarios that we have. Maybe, on a sewer pump, they milk cows, 400 cows in the summer and 800 cows in the winter. There's different operating points between those two sections. And so how do you identify operating points? And so we have a center pivot for an example. The white portion of the center pivot's at a 1060 feet elevation. The green hatched area is at a 1030. So there's a 30-foot difference across this field. And then as the pivot goes around, it's places right here, it's just the inner circle of the pivot. Well, maybe the pivot has a swing gun, and so in these sections of the field, it swings out a swing arm and does it right here like this and here. And then in some other sections, the farmer may have an end gun on the swing gun, and then he irrigates these corners a little bit. And so we have that right here and that. And so now I divide up my circle into pie pieces based on the section. So like number one is this section right here. It's just basically the pivot by itself. Number two right here is the swing arm without the end gun. Number three is the pivot, the swing arm, and the end gun. Now all these have different flows, so you can see right now at number one, and this is at different elevations. This is at my 1060 elevation, and this is at my 1030 elevation. So what you do is you're just cutting the pie into different sections based on what you see in the field. So all you have to do is draw a circle on the map where the pivot is, and you have to identify the different elevations and then the different flow rates. So here for section one, and notice that they could be different sections. So like here, this one is the same over here as it is over here. Of course, you could make a whole lot more if you need to. But here I just chose to do this up into 6 different sections. So number one, I add up all my ones, and the total degrees is 151. So 151 divided by 360, it's 42% of the area. My flow rate here is 600 gallons a minute. My head is at 138.6 feet. So my water horsepower is 21. And likewise, I do the same thing with number 2 sections of the field. And you can see the flow rate goes up, and so does the head. And then number 3, the same thing. And then the lower elevation area, as you can see, number 4 it's 125 for the same flow rate as it is over here. And this is all just due to elevation difference in that. And so I got my different operating points here that I need on the system. They range from 19 horsepower to 33 horsepower. So now I got a chance to, what somebody could do is they could program the variable frequency drive to match the pumping rates as the pivot goes around the field. And that this takes a little bit of programming. There's a little bit of take in this. So how this looks here, if you remember, we got our pump curve right here, and this is how it looks. And our operating curves are right here. And notice that the pump curve doesn't really fit the operating curve right now. This here is our full actually I think this is it right here now. And so now and so I got 2 operating curves, and the dark blue one is for an elevation of 1060 feet. The light blue one is for an elevation of 1030 feet. And so now what I'm trying to do is get my VFD down to here. And so I could use the pump affinity laws just to calculate what my percentage settings would be for each one. And so, and the spreadsheet does this, and we'll talk about that. And so here are the different affinities, RPMs, I mean, settings that we can have. Our pump at full RPM is 1600 RPM, and that sets us right here. So, so like this pump curve, this setting will be 1561 gallons a minute, and I think it's this line right here. And so you can see it goes right onto our demand point, and so you can lower this curve down accordingly. And so here, this one is the same table, but it shows our water horsepower here with our RPM speed right here to meet each of these zones on the field. And so we have the VFD economic calculator spreadsheet, and I go ahead and enter this in, and I put my operating points right down here. And so maybe I could go over this a little bit. In this section, you put your field size, you put your system flow rate, and you put the gross irrigation requirement for the year. Typically in Wisconsin, this is 11 inches. And what this will do is it will calculate how many operating hours you need based on this flow rate and this field size. Then you come over here and you put your pump curve from the manufacturer curve. You just put it just exactly like what is in. You put your RPM right here. Okay. So then in this section, you put your operating points. And so if I go back here, here's my operating points. I got a table based on the circle I drove and all the operating points that I found. And I got my Q here, my H here, and then I got, so here in this section, I put my Q and I put my H. And then I push this button that says find, and it will actually come here and calculate the VFD frequency needed, and also the pump efficiency there in that. And so then I go to this next section and do the operating hours. Well, it needs to know the percentage of the field. So if I look at this, if I look at this, I got my percentage of the field. It's, remember, we're just cutting the pie. And so you just divide it by the degrees by the 360. If you have a half pivot, you divided the total degrees by 180 or whatever that, pivot circle circumference is. And then, so that's your percentage of area. And so you put those down here. So operating point is 42% in that. And what that will do is it will calculate your kilowatt hours, because there's 65 horsepower for this section, meaning that it operates at 600 gallons a minute times 230 feet divided by the efficiency. That should equal 65 horsepower. There's your kilowatt hours. And then it spits down here time. And typically a VFD has a life of 10 years. And so in this case, this VFD would not meet our criteria for a cost share on multiple points. One thing
Mike-
I've seen, yeah, go
Mike,
ahead.
there might be one question out there. REA, did you have a question? I saw you unmuted. Maybe not.
Okay, one thing I've seen in the reviews I've done in Wisconsin, because we only put on 10, 11 inches, it's very hard to justify a VFD, in that you really need to have a field with a great, a large elevation difference. And that, I mean, it's good to go through the exercise for the landowner, but you'll get a feel of what's going to pass and what won't pass just by looking at it over time. In that, and so the VFD capital cost is right here, and that's what kind of comes back here is our savings. And you can see our energy savings is not, you have to calculate the 25% by taking a look at annual power use, divide, this one right here with the new with the new VFD with this one right here. So the other thing, Bethany mentioned that this VFD has an efficiency, and right here you can look at it. If you click on these red triangles, it will give you some things to look at, or defaults to put in there in your planning process. You don't have to be exact here. So these are assessment overviews, and so when you're going to an irrigation system, you're looking at use of water here on number 1, and that's using our tool called Fury. And I don't have it in here, and I probably should modify these slides before I send them out. The 449, our irrigation water management, that spreadsheet we build, the WIS or the WISP, is also helps us look at consumptive use in that. And so we really should put, I'll throw in some slides in on this since we discussed on that, and that's a good point Steve brought up. Then the next 2 parts is the energy parts of it, and that's the pumping system, and then seeing if there's any multiple reduced energy use. I want to say here, this is a lot of work for an energy audit, especially when you're looking at dryers and tractors and lights and stuff like this. And also the guy has 5 irrigation pumps, and if you're a consultant, you're swimming in it now, because this is a big job, a big work. And so that DIA that we had, I can't remember the number, is a tool that can be used to do this for irrigation systems. And I think it's something that can be done. And the assessments seem complicated, but really it's just a pumping system, and that's all you're looking at. And it could be, with a little bit of training, people could do this. Again, our references for irrigation practices, there's a whole bunch. NRCS is the leader in it. I think everybody out there goes to NRCS references. If you read a textbook, they've probably gone to NRCS to get all their stuff. And so they're written by good people, and they're applicable to our situations here. So with that said, I think I made it within our time. And so is there any questions or any comments you want to say?
There's one question that was received earlier, and it says 6.3 gallons per minute is needed for the pivot. But if the landowner wants to only irrigate at night, so only 12 hours, then a higher flow is required to allow the whole field to be irrigated in 12 hours instead of 24. More of a statement than a question, but I think it's something definitely you have to be taking into account what that system need is, how quickly that water has to get there, because it's not just at night that might come into play. There are other, in the micro irrigation, definitely, if I don't have enough water to cover the whole area and I need to move that around, that definitely could come into play of how much water do I need to get there, how quickly.
So that's an interesting question, Beth. We got to be a little careful there. The only water savings you get at night is you don't get your evaporation loss. And maybe with the deep humidity here, I don't know how that works, but you reduce your evaporation loss, which is usually 5%. So you only get a 5% energy savings. when we irrigate, we're trying to meet ET. ET does not change whether you irrigate by day or by night, because the plant is always evapotranspiring the same regardless what time you irrigate.
It's not how much water they're savings because of the cost of energy, because sometimes energy
yes, okay, so you increase your flow rate.
Yes.
So you could irrigate in those low energy savings times.
Yes.
Yes, that is correct, but you're still, so in that case, what we do is we speed up the pivot. Because we're trying to apply the same inch across the field, we're still trying to meet ET. But sometimes our design flow is around that pumping rate, and that's a good observation. And that's
it also comes into play even on big pivots when one pump services several pivots out there. That they might need to make sure that they have enough flow that they can water them quickly enough that they can get around to all of the pivots in a reasonable amount of time.
That's correct, and because they're trying to meet a pumping duration.
Correct.
In that, that's called scheduling the pump. Yeah, that's correct, and that happens. One thing I've seen in Wisconsin is a lot of people are under irrigating, and I'm not broadly sure how to do that, because it's not necessarily a bad thing here because we get so much rainfall. Irrigation is supplemental, and so that's some work maybe to do with our national standard and our national people is it something we cost share with? Because the way we calculate consumptive use, we are assuming there's no irrigation, no precipitation in that. And so sometimes I wonder, we may not have the supply that meets the demand. And you just mentioned some guys trying to irrigate multiple pivots off one well. He's probably deficit irrigating a little bit. And so, but I don't know if that's necessarily a bad thing in Wisconsin, because it's just a reality of the precipitation that we get.
I was gonna say, I don't know if they're even deficit irrigating at times, because there are systems that I've been out on site, they've literally used the system 2 times a year. So it's for very specific times that they need to water at time. They're not at a schedule all the time like that, but when they need it, sometimes they need to be able to go quick enough that they can get it around to all the systems that they need.
Well, that's correct. And so our standard is that our supply meets our demand. And so our demand's a little bit different here. We calculate what the ET is, but the precipitation meets like 80% of the ET demand. And so what we're trying to do is just hit those 2 times of the year when it doesn't. And so that's what I mean by deficit irrigation is it's okay. I wonder sometimes if it's okay to have a system on paper that shows deficit irrigation. And so that's a question I'm looking at from national people. Any other questions?
Yeah,
and if you don't, go ahead, Steve.
Yeah, I just wanted to kind of throw out, you provided a nice clear message that VFDs manage multiple operating points, and Brittany brought up the fact that that advantage also can come with a price, because if you move that operating point along the pump curve, you're going to lose some efficiency. And then Mike kind of countered back and said, well, that's true, but managing multiple operating, there's more, and there can be, and according to your source, there can be more long-term energy savings in properly managing multiple operating points than there is shifting along the pump curve. So I just kind of wanted to highlight that argument, because it's a site specific deal, and so it's just good that everyone's aware of it. So I'm really glad the conversation took place. in that arena of multiple operating points, Mike, I sure liked how you carved the field up to help develop those multiple operating points to evaluate a VFD. The other place that we can look in that, and I just don't know how big of a problem it is, but it's in the wellhead itself. Pulling 500 gallons a minute out of a well is no small thing. And the head, sometimes people think that the production tube in a well is you stick a straw into an infinite pool of water and it never moves. The static water level is always the same. And the reality is sometimes the aquifer is moving, 20 to 50 feet, depending on the draw of the pump itself, and also due to seasonal changes, depending on where you are in the landscape. And when these well drillers drill these wells, at least in my experience, you hardly ever get a 48-hour pumping test to identify where the drawdown level is for your design flow rates. You hardly ever get that. They claim they're doing a test, but all they're really doing is just they're developing the well and the well pack around the screen. They're doing basically what they call a Baylor test, and they're just pumping it out on the ground to help clean out the well and develop the well. And at the same time, if they shovel the water spewing out of the hole with their air test, they usually develop the well with like an air test. They take a guess at the yield of the well, but it's not a formal pumping test. So what I'm trying to say is that static water level in the well isn't static and it's moving around, and that could be a multiple operating point. And some of the well drillers, instead of spending money on a pumping test, they accommodate that cost savings to them by recommending and pushing a VFD, because that covers all if the static water level in the well moves 20 to 50 feet throughout the season or due to the level that you're taxing it, well, that takes him off the hook of having to do a formal pumping test, because hey, you put a VFD in there and that'll accommodate all of that. So I'm just saying, in the big picture, when you're sitting there trying to sharpen the pencil on all the energy and you're breaking the field into zones, but you're completely unaware of the fact that you could have a 20, 30, or 40-foot head change in the well itself, in the water supply, I think that kind of needs to be factored in too. And we just don't know it. And I think it'll help, Mike, because Mike, we ordered that flow meter, right?
Yeah.
So that should help us a little bit identify what the current pump is pulling out of the well at a couple of different operating points anyway, in terms of what's out in the field, so you can kind of detect if you have major changes in your water supply. But I don't know, I just wanted to throw that out there, that multiple operating points comes in different forms.
Very good, Steve. And the essential in our system here is the elevation of the water supply, and what we're looking at is the low water level in a stream, reservoir, or a well. And these fluctuate. I think they fluctuate more seasonally in a pond. Summer goes down, winter goes up in that. And wells over time, they will fluctuate as well. And so we need to be mindful of that. And so Steve brought up a good point that we are going to have a portable flow meter that you could strap onto a pipe right here. And we could go out in the field now and test what this well's able to produce, or what this pump is produce. That's a big uncertainty that I've seen is, well, what does your well do? And nobody really knows. We have the well test from the DNR, but that's not based on a 48-hour drawdown. in that. And so this one actually gives us a good indication what that well could produce. If we get a flow rate and we got a pressure gauge, we could actually see what it is on the pump curve, and we could see where this pump is actually performing on the pump curve. And so we now have the tools with the operator usually has a pump, a pressure gauge, and now we have a flow meter that could be at the state office that can be taken out there in the field and used. So just thanks for advertising that, so Steve, so people want to know that that's available.
Yeah, for like a municipal well, which pulls a lot of water, you know, they drill 2 holes, right? They drill a 6 or an 8 or a 10-inch production well, and then they drill another monitoring well off to the side, and then they pump it for 48 hours at varying they're pumping out of one well at variable speeds, and then they're monitoring the head drop in the other well. And so they're coming up with a yield curve for the well. That's expensive to do. There are some abbreviated ways of just testing the hole after it's been drilled using a variable pump test. But I just don't know how serious to get about it. I just don't know how serious to get about it, because it does concern me that that could be a significant factor in the pump design, and we're overlooking it. So I don't know. Maybe I'll if you guys just be aware of it. Just be aware of it, I guess, and maybe give me some feedback over time. We can also purchase an ultrasonic well depth, instead of the resistivity tip, where you lower a cable down in the well. That's pretty tough to do when the well's running, right? When you got a turbine pump and it's running and there's no access to the well casing. But they also make an ultrasonic one. So we could get that static water level in the well if we need to. Mike, if you feel like that's a critical piece of information that we're missing, they're not that much money.
Okay, we'll look into it. I think, we really haven't done pump tests, and sometimes the pump tests really tell us what's happening out there. It's a good way of evaluating. Otherwise, you're just locked to your manufacturer curve, and it's really hard to assess whether the well could do it or not, and what's happening.
Like that, I don't have any other questions within the queue at this point.
All right, well, let's stop the recording then, and I guess I appreciate everybody's time. This was a fun project, and I have to acknowledge Matt Lahoyak, Doug Dank, and